Okay, sorry. Okay, so I hope I'm audible. So, good evening, everyone. So, you guys have your pre-RMO tomorrow. So, how is the preparation going? I mean, I hope those of you who are appearing for it, at least you have gone through the problems of number theory. And so, let's today discuss a few other tricks that might help you tomorrow. So, like finding, like evaluating telescope sum expressions and others. So, so for those of you who don't know what a telescope is, right? So telescope sums. Suppose you are given a expression, like say suppose S equals sum over I runs from 0 through n, or let's assume it's 100, uh, 1 by k times k plus 1, or I times I plus 1. So how do you evaluate one of these? Any guesses? Anyone? I see just three of you are here. So, or Chishman, can you unmute yourself and give a guess or something how to solve this one? Hello. Oh, okay, whatever. So you most of the time in these situations, you try to write the expression inside the sum as a difference of two sequences. They're just in terms of two sequences. Like for example, here you may write it as 1 by I plus 1, 1 by I minus 1 by I plus 1. So this 1 on the top, on the numerator, you write it as I plus 1 minus I by I plus 1 times I plus times I. And then you distribute it. So you get I plus 1 by I plus 1 by I times I plus 1 minus I by I times I plus 1, which is equal to 1 by I minus 1 by I plus 1. Okay, see, I gave the bounds a bit wrong. So this can't start from 0, obviously. So let's make it from I equals to 1 through 100. Okay. So now you have this, you can take it as pi for some, where pi is defined as 1 by I, and automatically the second term becomes pi plus 1. So this is basically a sum of the difference of the consecutive elements of some sequence p. Now what you can do, you can uh, write the sequences in pairs and then cancel out, and you will see able to see things get cancelled out. So p1 minus p2, p2 minus p3, and like this up to pn minus 1 minus pn and pn minus pn plus 1. So this is basically the sum written in the expanded form. Sorry, and you will be able to cancel out the terms like this in diagonally. So you get p1 minus pn plus 1 as the end result. So you are able to like get the value of s without explicitly computing all the 100 terms. So this method is called the method of telescopes. And this was simple in this case, but in other cases, this might not be this simple. So let's go through a few cases. So question one. Right. So the example we just saw is this example. 1 times 2 plus 2 times 3 plus 3 times 4 dot 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 up to 1 minus n, 1 by n minus 1 times n. This is the first example. The next problem is this. What if you have three terms? So 1 by 1 times 2 times 3 plus 1 by 2 times 3 times 4, like that up till 1 by n minus 2 times n minus 1 times n. So what is this sum equal to? In this case, obviously you have to first express the sum in the summation notation using the capital sigma notation. So I equals to 1 through n minus 2, 1 by I minus, okay, let me write it as from 3 to n minus 3 to n. So now I can use I minus 2, I minus 1, and I. So whenever you have this case, like the general term looks like some product of adjacent things on the numerator and some other product of adjacent things on the denominator, you kind of have to take uh, like if you don't have the numerator, like if the numerator is just some constant or is one, you will always be able to take that constant out of the summation. So you can basically think of one case where the numerator is one and the denominator is the product of some consecutive things or some may not be consecutive, like it can be in AP also, but they have to be in constant intervals. So the difference between these two has to be D, this two has to be D. Like here we can see this difference between them is 1, and so is the difference between them. In this case, you have to multiply, right? Multiply like I minus 2. So look at these two terms, the the first and the last one. Suppose the first one is like uh, I minus kd, and the last one is I. So then multiply and divide by I minus kd, which is basically kd. I'm just writing it this way to help you understand how am I getting the kd thing. And also in the denominator. So if you do that, in the next step, you will get, so we can take this thing, so basically kd. So we can take this kd constant out of the summation here. Then we will get, sorry, then you will get I by I minus kd times I minus k minus 1 d dot 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 up till up till I minus I minus kd by the same thing. Cancel out I here and I minus kd here. You get 1 by I minus kd times I minus k minus 1d up till I minus 1, I minus d, sorry. The common difference is d in this case. Like I have assumed a generalized case. So, and here you will get 1 by I minus k minus 1 d times up till I. Now you will take this term as your pi minus d and this term as your pi. And then proceed the same way as I did in the above one. Just here the consecutive pairs won't get cancelled. So if you write them out, you have like 0 minus d minus p0, p1 minus d minus p1, and like that up till pd minus d minus um, pd, right? So this is 0, basically. This is p0. So let me write it as p0. So this p0 and this p0, they get cancelled. And similarly, the next p1 and p1 will get cancelled. So you will be left out with these things above p0. And similarly, like there will be d minus 1 things, I guess, and similarly there will be d minus 1 things. So that whole expression containing n things, you will be able to reduce it into 2d minus 1 things. So that's what telescope is there for. So for in this particular example, you will get uh, right. So it's half is the, okay, let me write it down. So it's sum over, you will take the difference of the first and the last, I minus 2. I runs from 3 to n, and then distribute it. So it's 1 by I minus 2 times I minus 1 minus 1 by I minus 1 times I. So you get, so this is our pi minus 1. This is pi. So you get, this starts from I equals to 3. So p2 minus p3, p3 minus p2, so on up till, oh, sorry, this is p4, up till pn minus 1 minus pn. They get cancelled like this. You get p2 minus pn. So p2 from our definition is 1 by 0 z, no, sorry, it's 1 times 2, right? So just remember here, so pn is defined as, looking at this, n minus 1 times n. So p2 is 1 times 2 and pn is n minus 1 times n. So we got our answer. Oh, by the way, sorry, I forgot to take the half common from here, since this, we remember we have to divide and multiply by kd. So kd is 2 here. So here you have a half outside times half times half times half minus 1 by n into n minus 1. if we take the LCM, it's it's nothing like beautiful or something. It's something like this. If I simplify it further, this is the answer. Right, so this case is done. Moving on, we have the second kind of sum. So here you have the numerators. So, like for example, 1 times 2 times 3 plus 4 times, sorry, yeah, that can be a problem, but we'll deal with it later. So 2 times 3 times 4 plus 4, 3 times 4 times 5, like that up till n times n plus 1 times n plus 2. So what do you do in this case? Now we can write the sum S as, so S is this sum. We can write it as I runs from 1 through n times I times I plus 1 times I plus 2. So whenever you have just the denominators in some constant difference t, like I plus, like I times I plus t times I plus t plus I plus 2d up till I plus kd, and in the denominator you just have a 1. You have to take, you have to divide and multiply with the, I mean, with the over boundaries. Like, what is the term before this that is missing? This is, of course, I minus d. And what is the term after this that is missing? This term is I plus k plus 1d. Right, so you have to multiply and divide by that. So let's see how this works with this example of ours. So we divide and multiply it with I plus 3 minus I minus 1. Right. So what is this thing? It's 3 minus 3 plus 1, right? 4. So this thing is 4. We can take the constant out. So 1 by 4 times I runs from 1 through n. I times I plus 1, I plus 2, multiplying it with the first factor, I plus 3, multiplying with the second factor, minus. So this is, everything is under the summation. I times I plus 1, I plus 2 times I minus 1. Basically, I have to rearrange this a bit. So yeah. So now you can observe this is, identify this as pi, and this is pi minus 1. Now it's the same old telescope. Sorry, why did I write n here? It's 4. So 4 times, so this thing starts from 1. So P1 minus P0, okay, P2 minus P1, Pn minus Pn minus 1. So this thing cancels in the uh, left diagonal way, so kind of interesting. So you get 1 by 4 times Pn minus P0, and by this definition, you can see Pn is n times n plus 1 times n plus 2 times n plus 3. So this is P0 is 0. So it's 1 by, uh, so it's n times n plus 1 times n plus 2 times n plus 3 by 4. So S is this. I hope this technique was clear. It's pretty easy to follow too. You just have to remember these two ways of taking the telescope. There are trickier ways the problems can pose, like what if both of them are present? Take this example. Okay, this example is not here, so I will just make up one. So 1 times 2 by 3 times 4 times 5 plus 2 times 3 by 4 times 5 times 6 dot 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 like that up till uh, let's say n minus 1 times n by n plus 1 times n plus 2 times n plus 3. So what is this sum? Say the sum is S. It's a solution. So S can be written as sum over I runs from 2 through n, I minus 1, I plus 1, I plus 2, I plus 3. So here in this case, when you both have a numerator and a denominator greater than 1, and all of them are in AP, so right, suppose the numerators are I minus D1, I minus, okay, sorry, I minus K D1. Oh, we have to use K1 also, right? So I minus K1 D1, I minus K2, sorry, not K2, K1 minus 1 D1. Let me write it here. Up till I minus D1 times I. And in the denominator, suppose you have I time or I plus D2 times I plus 2D2 up till I plus K2 D2. So what you do here is you take the next term, whatever there is, and the and this term I. Sorry, I guess I told the reverse. So you take this term, this one, the end one, the largest one from the denominator, and the next term of the numerator. This is, of course, I plus D1 here. So you multiply and divide by that. So just so whatever we had, then you multiply it with I plus d1 minus I plus k2 d2 and divide by the same. This is just a constant factor, so you will take this factor out of the sum, and then you will see how this thing helps us to find the, like, divide it into, like, write it as a difference of two polynomials. So let's see that. So this sum, right? So here, according to our result, we should take the difference of this thing, I plus 3 minus I plus 1. So what is this? Basically, it's half. So half times I times I minus 1 times I plus 1, I plus 2, I plus 3, I plus 3 minus I plus 1. If we multiply these into this and this, we get I plus, or I minus 1 times I. The I plus 3 thing gets cancelled, so we are left with 2 in the denominator, 2 product terms, minus I minus 1 times I plus 1, and I plus 1 times I plus 2 times I plus 3. Okay. So just a minute. Did they get the terms increase, right? So if we take this as pi, is this pi plus 1? Not exactly. This is a different polynomial, right? So just a minute. So here, instead of taking the difference, what if we had done the same as the numerator? So if we write it as I plus 1 minus I minus 1, the denominator won't change, right? Okay. Oh, okay, I get it now. So we have to take a fraction instead. Oh, sorry. this I plus 1 is getting cancelled, right? I didn't notice it, sorry. That shouldn't be the case. So we have I times I minus 1 or I minus 1 times I and I plus 1 times I plus 2 times I plus 3, and similarly same thing here. So how can we multiply things so that they still remain equal? So if we multiply I plus 1 here, this thing gets cancelled. Okay. So if we multiply it by I plus 1 by um, this one, smaller one, that is I minus 1 minus I minus 2 by I plus 3. Sorry, this is I plus 1. This is no longer a constant. What should we do? Uh, if we take okay, if I take I plus 4 and I here in the denominator, no, how will I cancel them? I have to cancel one factor from the denominator here, one and a factor in the numerator here. Okay, so uh, I have gotten the exact the exact multiplying factor in this case. So we will leave this for now. It's wasting a lot of time anyways. So and this case is actually pretty rare to encounter. So we will now move on to some examples and then the product case, like the product telescopic sums, telescopic products. So example number one. So all right, this square root one is pretty common. System. All right, so here is the sequence: one by square root of 1 plus half, square root of 2 plus 3, square root of 3 plus 4, like that up till 1 by square root of 99 plus 100. So how to solve this? So this is the S is equals to I runs from 2 to 100, square root of I minus 1 plus square root of I. You can of course try to rationalize, and this is actually also resulting in a telescopic sum. So we're multiplying with the conjugate surds. You get square root of I minus 1 minus square root of I. So that's just root 1 minus root 2, root 2 minus root 3 up till root 99 minus root 100. So they get cancelled. You get uh, root 1 minus root 100, 1 minus 99, and 1 minus 10. Just a minute. Okay. So here I like the denominator. This would have been I minus 1 squared minus I squared. Sorry, I mean this is square of the square root, so it's I minus 1 minus I. So this is minus 1. So here we have a minus 1 outside. So that's why this is minus 1 of root over 1 minus root over 100. This is then plus 9. Right. Okay. Next, try this example. So So you know the Fibonacci series, right? The Fibonacci series is given by f0 equals to f1 equals to 1. And then from 2 onwards, we have fn equals to fn minus 1 plus fn minus 2. So writing down the series out, we get 1, 1, 2, 3, 5, 8, 13, and like that. So just the sum of the previous two terms, like that. So this is the Fibonacci series. So now find this sum. 1 times 2 plus 1 times 3 plus, just a minute. Okay, so this is right. 1 times 3 plus 2 times 5, 3 times 8, and like that. So get it right. It's basically irons from uh, 1 through n, 1 by fi minus 1 times fi plus 1. So try to simplify this sum using telescope. I will just give you 5 minutes. Till then, let me also try to solve this one that I was trying to. So meet you after 5 minutes. So I'm back. Hello. Yeah. So any one of you could figure out the trick? Like as you can see, the difference of the consecutive terms in the denominator aren't constant now, since this is not an AP, it's a Fibonacci series. So typical way of solving won't work here. So here you have to first multiply the denominator numerator with fi with fi. So fi by fi minus 1 times fi times fi plus 1. So we multiplied the numerator and denominator with fi. Now, from the inequality, from the Fibonacci reconciliation, this one, we know that fi plus 1 equals fi plus fi minus 1. So taking fi on one side, we get fi equals to fi plus 1 minus fi minus 1. So we replace the I in the numerator with fi plus 1 minus fi minus 1. Now you can see the telescope. The first term after distributing is 1 by fi minus 1 times fi minus the second one is the fi minus 1 gets cancelled, fi times fi plus 1. So this is pi, this is minus, it's times, so it's pi plus 1. Or let me call this pi and let me call this pi minus 1. So it's from I equals to 1 through n. So p0 minus p1 up till pn minus 1 minus pn. So this is p1 minus p2, right? So p0 minus pn, p0 is, so p0 is 1 by, okay. So here, according to our definition, pn is equal to 1 by fn times fn plus 1. So this is 1 by f0 times f1 minus 1 by fn times fn plus 1. f0 is 1 and f1 is 1. So both of them are 1. So that's why this is 1 minus 1 by fn times fn plus 1. So that's the answer. So this was one of the unique examples. Now, let's see next one. So this is like s equals to 1 by 2 squared minus 1, 1 by 4 squared minus 1, up till 1 by 1000 squared minus 1. How will you get s? So s is basically I runs from 2 through 1000, 1 by I squared minus 1. You can write this as I plus 1 into I minus 1. And now the rest is simple. Just you can obviously write this as you have to multiply it with I minus 1. Sorry. I plus 1 minus I minus 1, that is half. So you have to adjust with half, and then you will get some telescope. This was pretty simple. So there are a lot of variants like this. Let me try with, okay, so this one looks interesting. So for that, first you have to know some binomial coefficients, and okay, let's talk about them. So here are a few formulas for series and sequence. So I hope you all of you know how to find the sum of the first n natural numbers. That is sum over I runs from 1 through n, I. So this is n into n plus 1 by 2. So the way we do it is like we first take the sequence as s, then we reverse it 1 n plus n minus 1 up till 1. And now we observe adding the terms, you get n plus 1 everywhere. So how many terms are there? N many. So this sum is basically equals to 2s equals to n times n plus 1. So that is s equals n plus n into n plus 1 by 2. Similarly, not exactly similarly, but using similar tricks, you can derive 1 plus 2 squared plus 3 squared plus 4 squared like that up till n squared equals to n into n plus 1 into 2n plus 1 by 6. Uh, I guess an easier way would be, so s equals to sum over I squared. So first observe that what happens when you take the difference of two consecutive cubes. Suppose you have n cube and you take the difference of n minus 1 cube and n cube. Sorry. This is n cube minus n cube minus 3n squared plus 3n minus 1. So n cubes gets cancelled. That's 3n squared minus 3n plus 1. So 3n squared minus 3n plus 1. So this is n cube minus n minus 1 whole cube. Now we have to take summation. Okay, let me change the variables. So I cubes minus I minus 1 cube, 3i squared minus 3i plus 1. Let me take summation I runs from 1 through n on both sides. So you can see a telescope on the left, and on the right we get 3i squared, the sum that we wanted, minus the sum that we know already, 1 through n. And this last thing is basically just n. So this is n. This is n into n plus 1 by 3 times that. And now this is also like this is 1 cube minus 0 cube, 2 cube minus 1 cube, up till n cube minus n minus 1 cube. So they get cancelled like this. We're left with n cube minus 0 cube is 0. So n cube equals to 3 times x, or let me see sum that we want to know, minus 3 by 2 times n into n plus 1 plus n. So we get 3s equals to n cube plus 3n into n plus 1 by 2 minus n by 3. So s is this. I guess simplifying we will get our result. So we already got 6 in the denominator. This is 2n cube, sorry, plus 3n squared, 3n squared plus 3n minus 2n. So we have 2n cube plus 3n squared plus n by 6. We can take common n. 2n squared plus 3n plus 1. And you can, of course, do a middle term factorization. Guess it's n plus 1 into 2n plus 1. Right. So that's it. Next, for a simple exercise. So this is an exercise. Derive the formula for the biquadratic sums. So 1 power 4 plus 2 power 4 plus 3 power 4 like that up till n power 4. What is this? I will be back in 5 minutes. So if you're already done with it, let me let me do it again. So you just proceed in the same way. You observe that n cube minus not n cube. Oh, so we haven't derived the cube yet. No, no, don't worry. So we have to do with n5 minus n minus 1 power 5. Pretty large. So it's n power 5 minus n power 5 minus 5 times n power 4. Yeah, plus 5c2, that is 10 times n cube minus 5c3, that is again 10, then minus and then plus 5n, lastly minus 1. So as always, the largest degree gets cancelled. You have 5n4 plus 10, sorry, minus 10n cube plus 10n squared minus 5n plus 1. Change of variables and summation 1 through n. I5 minus I minus 1 whole power 5. So 5 times I4, 1 through n. This is what we wanted. Minus 10 times I cube, 1 through n. Actually, to compute this, we first have to compute the sum over the cube of the first n natural numbers. So that I will assume we have already calculated. So next we have 5 times, no, 10 times I squared. Is it? Yeah, it's plus 5 times I and plus n. This is as always, this is 1 power 5 minus 0 power 5, 2 power 5 minus 1 power 5, like that up till n5 minus n minus 1 power 5. So this is n power 5. Therefore, n power 5 equals 5s. And here the sum is, I'm assuming we already know, is n into n plus 1 whole squared by 2 plus 10 times, this we already calculated, this we know is n into n plus 1 by 2 plus n. So basically s equals to n5 minus 10 times n squared n plus 1 squared by 2. So this is just 5 times that. Okay. This is plus minus 10. This is again 5 by 3 times n into n plus 1 times 2n plus 1 minus 5n times n plus 1 by 2 plus n. This whole thing divided by 5. So whatever it is simplifying, I'm not taking the trouble of simplifying it, since it's a pretty huge, bulky looking expression. Not much useful since you can't memorize it. And you don't even have to. Okay, so a lot of telescopes. Now let's see some product examples. So some product telescopes. Just a minute. So let's start with this one. Product of I runs from 3 to 100, I squared minus 1 by I squared minus 4. So what is this product? So as always, you first, so since it's product, let me take it as P. P is equals to product of items from 3 to 100. Using the a squared minus b squared formula, we have a plus b times a minus b by a minus b times a plus b. Now we divide it into two products, I minus 1 by uh, we take I minus 2. This is I plus 2 to I plus 1. Now we will use, now we will just expand and use forward cancellation. It's better to expand this horizontally instead of vertically like before. So this one, the first one expands to as 2 by 1 times 3 by 2 times 4 by 3 up till, so it's 100 minus 1, 99 by 98. This one cancels like this. And this one is 4 by 5 times 5 by 6 up till 101 by 102. So this one cancels like this. You get 4 by 102. This is 99 by 1. So this equals 99 by 1 times 4 by 102. And so this was pretty simple. A bit more complicated example will be more products. Okay, so most of them are similar, so I'm not solving the next one also. So let's move on to binomial coefficients. I mean, I will cover this topic in the future, but for today, we just like have a look at those sums which involve binomial coefficients. So, just for recap, NCR, NPR, this is also sometimes written as like this or even like this. So this is basically equal to NCR, this is N and this is R, is equal to N factorial by R factorial times N minus R factorial. It's N into N plus 1, sorry, N minus 1 times N minus R plus 1 by R into R plus 1, no, R minus 1 up till 1. So R factors on the numerator and R on the denominator. So this is NCR and NPR instead is N factorial by R factorial. Sorry, N minus R factorial. Right. So knowing these two, the binomial coefficients are the coefficients that you encounter when you expand things like uh, a minus b power n. So this is equal to sum over I runs from 0 through n, a power n minus I, nci, b power I, and minus 1 power, so it's minus b power I. Right, so I hope you all know this. If you don't, it's nothing, it's just a generalization of the a plus b whole square and a minus b whole square formula. It's like a n minus nc0, sorry, nc1, a n minus 1 times b plus nc2, a n minus 2 times b squared. So you see the sum of the powers of a and b remains constant. That will be true for the whole series. So if n is an integer, then the sequence actually is, the series is a finite series. Is a finite series. So it has finitely many terms, exactly n plus 1 terms. Right, but what if n is not an integer? What if it's oh sorry, this is not only integer, it has to be positive integer. So it has to be natural number. If it's a negative integer, so it's a negative integer, then this expansion can be modified to have infinitely many terms. Similarly, if it's fraction, like if it's rational. I'm not going into all those details. For now, so let's move on to the sum of binomials, binomial coefficients. So first, observe the first identity is NC0, NC1, NC2 up till NCn. This is equal to 2 power n. This can be shown using combinatorial arguments, or you can opt for other algebraic methods like sum over NCi, I runs from 0 through n. So this is what you want, right? Now observe that this is exactly the expansion of 1 plus 1 power n, like from the definition. Hence this is equals to 2 power n. Similarly, the sum nc0, nc1, nc2 minus nc3, this is equals to 0. Why is that true? since this is basically the expansion of 1 minus 1 power n, which is 0 power n. So this is minus 1 power I, and see I runs from 0 through n. Now an interesting observation. If you just take the even things, uh, it's like n by 2, floor of that times 2. This even things is equal to the sum of the odd things. Both of them are actually equal to 2 power n minus 1. So why is this true? For this, you actually need a bit of complex numbers for this. So I'm just showing the proof as a formality. So 1, 1 plus x power n. This has the expansion 1 plus nc1 x plus nc2 x squared up till x power n. Now we have uh, we want only the odd squares. Sorry, even squares for now, not squares. This one is basically NC0. Okay, we will use the two roots of unity. We will first put 1 here. NC0, NC1, NC2, NCN, power n, the 1 power n is 1. Next we put 0 here. Sorry, minus 1 here. NC0 minus NC1 plus NC2 minus NC3 up to NCN minus 1 power n. Now we add these two. You have 2 power n plus 0 power n equals to twice of the odd terms get cancelled. Right. So you have twice of NC0, NC2 up till whatever the last even thing is. This one maybe. You just divide this by 2 and you get the sum of the even things. This is 2 power n minus 1. Incidentally, you can do the same thing for odd 2 things. There's an easier way to see that. You see the sum of the odd plus even is the whole thing. That is 1 plus 1 power n, which is 2 power n, that is we all know. and we just prove the sum of the even things is 2 power n minus 1. That means the odd things sum up to 2 power n minus 2 power n minus 1, which is 2 power n minus 1 times 2 minus 1 and 2 power n minus 1. Right. And similarly, this was for the odd and even things. But if you have to find this one, like NC0 plus NC3 plus NC6, the ones that are congruent 0 mod 3 up to N, what is this? For this, you need complex number for sure. So this equation, x cubed minus 1 equals to 0. Solution of this equation are 1 omega and omega squared. These are called cube roots of unity. You may or may not be familiar with complex numbers. So these are complex numbers. Omega here is can be pictorially represented as points on the unit circle with exactly 120 degrees apart. So this is a unit circle. So this vector over here represents the complex number 1. This vector at 120 degrees represents the complex number omega. Similarly, this is also 120 degree and this is also 120 degree. This is omega squared. Using De Moivre's theorem, you will be able to see this omega is equals to cos theta plus iota sine theta. Theta here is the radians of 120 degrees, so it's like 2 pi by 3. So 2 pi by 3 is iota sine 2 pi by 3. I guess cos 2 pi by 3 is it's yes, it's minus 3 by 2 over 3 by 2. Iota sine 2 by 3 is 1 by 2. So this is iota minus root 3 by 2. Sorry, I guess I'm wrong. This is minus half and iota root 3 by 2. Sorry. So this is minus 1 plus root 3 iota by 2. Right, so whatever its value is, we don't care. We just care of the property that they all satisfy x cube, and omega squared is also the solution to this equation. So using that, you see, we know 1 plus x power n is this expansion. So it's this cube up till x power n. So first substitute omega here. Sorry, NC3, NC4, oh, sorry, I missed the square term. That's why it's why like I'm getting 4 here. This is 2, this is 3, right? Now we substitute omega squared. So NC0, NC1, NC2 omega 4, NC3 omega 6, up till omega power n and omega powers 2n. Now add them up. You have 1 plus omega plus, oh, we have to write one more. Now substitute 1 plus 1 plus 1. Now we add. Down the left, we have 1 plus 1 power n, 2 power n, 1 plus omega squared power n. We actually can factorize this using a cube minus b cube. So this implies x minus 1 into x squared plus x plus 1 equals to 0. And since omega is a solution, we know omega squared plus omega plus 1 equals to 0, since omega minus 1 is non-zero. From that, we know omega squared plus 1 is minus omega. That's why here, omega squared, 1 plus omega squared, we can substitute it as minus omega. So it's minus omega power n. And similarly, this thing is minus omega squared power n, or omega power 2n. So this is that. And on the right hand side, let me make it smaller. So 3nc0 plus nc1 times 1 plus omega squared, which we know is 0. It's nc2 times 1 plus omega squared, the same thing is 0. And nc3 times again 3. Since omega cube is 1, omega power 6 is 1, and 1 is already 1. So now you see these gets cancelled, right? They multiplied with a coefficient which is already 0. There's basically 3 times nc0, nc3, up till nc, whatever the last thing divisible by 3 is. N by 3 is box times 3. The thing on the left is a constant, I mean, in terms of n at least. So, so we can compute it. If we assume n to be odd, or okay, let's assume m to be odd or whatever it is. So it's basically this sum is equal to 2 power n plus minus omega power n plus omega power 2n by 3. Right. Similarly, you can use fourth roots of unity, fifth roots of unity, and all those after that to find the coefficients which are 3 apart or 4 apart. Let's move on to something even more trouble. Like what if you have sum and difference? Like this is what is the sum nc1 plus 2 times nc2, 3 times nc3, like that up till n times ncn. So to find this, let's first write it in compact form. It is I times NCI. There's something called, there are two important expressions. NCI is equal to n minus 1 by I minus 1. Sorry, n by I times n minus 1 C I minus 1. Similarly, if you take the, the cross product, it's n minus 1 C I minus 1 equals to n by I. Sorry, I mean by I by n times NCI is this. If you further replace n with n plus 1 and I with I plus 1, then you get NCI equals n plus I plus 1 by n plus 1, n plus 1 by I plus 1. So remember this, and this is uh, the forward deduct, the backward deduct. Using the forward deduction for now, so the backward deduction for now, we get NCI is equals to n by I minus 1 CI minus 1. The I gets cancelled, the n will constant, we can take it out. N minus I C I minus 1. And we can do a change of variables. Let me replace I minus 1 with I. I runs from 0 to e minus 1, e minus 1 ci. This is just n power n times 2 power n minus 1. Excellent. Then let's do this one as an exercise. S equals to 1 into 2 into NC1 plus 2 into 3 into NC2 plus 3 into 4 into NC3, like that up till n into n plus 1 into NCm. So as before, we write S using the summation notation. So it's I into I plus 1 times NCI. And here you have to use the backward reduction twice. This is the forward reduction. So using it once, we get n by I times, again using it once more, we get n minus 1 by I minus 1 times n minus 2 ci minus 2. This I and this I and this I plus, oh, this is an I plus 1. Sorry. Oh, sorry. I can't use a backward reduction then. So then at least we can do it once and then we have to break it out. I plus 1 I into n by I times n minus 1 ci minus 1. Take the n out. Now we can write I plus 1 and I minus 1 plus 2. And now break the sum into two parts. The first part is with I minus 1 factor, and the second part is just the n minus 1 ci minus 1. This is just 2 power n minus 1 from the previous calculation. Right. And now in this first part, we can use the second backward reduction. So again, n minus 1 is a constant. We bring it out. So twice n times n to power n minus 1. And this sum, we do a change of variables. We write n minus I minus 2 is a 2 as I. I runs from minus 1 to n minus 2. This is n times 2 power n. So nc minus 1 is n minus 2, c minus 1 is basically 0. So instead we can assume it's running from 0. So we drop the first term as it's 0. So it's n into n minus 1 into 2 power n minus 2 plus n into 2 power n. We take common n into 2 power n minus 2. It's n minus 1 times n minus 1 plus n squared. So it's n into 2 power n minus 2 into n plus 3. Right. These sums are pretty routine and straightforward once you uh, see the basic tricks used here, like change of variables, uh, this identity. There are a couple of more identities which I will binomial identities. So let me list a few of them. First is we have the Pascal's identity. So NCR is equals to n minus 1 CR minus 1 plus n minus 1 CR. Second, we have these two. Second and third is done. Okay, let me write them down. So NCR is n minus 1 n by r times n minus 1 CR minus 1. And NCR is r plus 1 by n plus 1 times n plus 1 by r plus 1. The fourth one is um, I guess NCR is equal to NCR minus n minus r. Fifth one, okay. Fifth one is if you take this sum, I runs from 0 through n, NCI times NC n minus I, NCI squared, the same as NCI squared using this identity. This is equals to 2NCN. I guess this is enough for this class. So best of luck for your exams. See you next week. Bye.